Okay, hello Spring 2026 Gen Chem 1 students. I wanted to take some time to show you a little bit of what these AI assignments can feel like. I first want to point out that when I went to DOT and I plugged in my learning objectives using the prompt that was provided, DOT started to give me information that spanned all semester. I recognized that as the instructor, that this was far beyond the scope of what this learning objective was supposed to be. So I went back to DOT and I plugged in the same learning objective again, and I asked it to keep it in the context of Unit 1. Now I'm going to point out that even while doing this, it actually didn't do the best job of keeping things within Unit 1. And DOT is an AI program that's, in theory, trained only on your Real Chem textbook. So I will be transparent and say that if you are struggling to solve any of these AI problems, the benefit of doing the pen to paper work goes out the window if you're spending too much time trying to learn things that aren't in the context of that unit. So I'm gonna need you to use some discretion and say, there are things here that I know I have not covered. They were not in the textbook. They do not resemble what's in the checkpoints. And for that reason, I'm gonna pass trying to solve them. And I'm gonna prioritize the other examples that really do hit on the material that I'm reading in Real Chem and the material I'm seeing on my homework, the checkpoints. Okay, so first I'm going to skip question 1, which says convert mass from grams to moles. This is something that comes up a little bit more in Unit 2 and then later in the semester as well, and it's not something that you will do in Unit 1. Instead, I'll give you an example, a diagram converting volume from milliliters to liters. So some people will refer to this conversion as a bridge. On that bridge, we should expect to use a conversion factor. A conversion factor should have at least 2 units. In this case, the 2 units will need to be milliliters and liters. There's a few ways that you can write conversion factors. For instance, you could say that 1,000 milliliters is 1 liter. And you can use this hyphen to say that this is a relationship. A more useful way to write it is as a fraction. 1,000 milliliters is 1 liters. But I do want to point out you run into an issue early on, which is there's no right answer for which value should be on top and which value should be on bottom. Both of these conversion factors correlate 1 liter to 1,000 milliliters. There's another issue that arises here, which is that I've chosen to keep 1 relative to liters, and 1,000 is the number I need to use for milliliters. But there's no reason that I can't report this as 1 times 10 to the negative 3, 0.001 liters is 1 milliliter, which again gives me another version where I put liters on bottom and milliliters on top. These are the same conversion factor. In my lectures, I've mentioned that whatever unit is larger will always have a smaller value with it, and whichever unit is smaller is always represented with a larger number. So there are fewer liters in a larger amount of milliliters. Less than 1 liter in 1 milliliter, 1,000 milliliters in 1 liter. Big unit, small number. Small unit, big number. So these are all for the same exact conversion factor relating milliliters and liters. How you want to use it depends entirely up to you. I guess a third way that you might see this fraction written is that instead of a decimal point being written, you might see it written in scientific notation. If the decimal point has been moved 3 places, then the exponent on 10 represents that. So let's do some dimensional analysis. These were the problems that the AI gave me based on the learning prompt for how to use dimensional analysis in doing in our problems for Unit 1. So I want to go through this problem. A label states that a serving of cereal contains 30 milligrams of sodium. Convert this quantity to grams using dimensional analysis. One thing that I want to point out to you guys when you do dimensional analysis is that you'll often have a piece of information that has 1 unit. This is where I like to start. I'm going to begin my calculations with this piece of information with just 1 unit, because there's only one thing I can do to it: cancel that unit. Then I need to look for information with 2 units. Remember, conversion factors are pieces of information with 2 units. I'm not given a conversion factor, but as soon as I write out 30 milligrams, I can see a conversion factor. I can place milligrams on the bottom, and in the end, I want to get to units of grams. I'm not sure what the number will be just yet. So if I need to cancel milligrams, I'll need to multiply by 1 over milligrams. And if I want to end in grams, I need to multiply by grams on the numerator. By plugging in just my units, I can see that milligrams cancels. I'm left with grams. Now I need to relate 1 gram to 1 milligram. Sorry, grams to milligrams, which is the same ratio as liters to milliliters. So I have a choice. I can put 1 with grams, 1,000 with milligrams, or I can put 1 with milligram and 1 times 10 to the negative third with grams. I generally tend to stay away from scientific notation, so I'm going to say 1 for the big number. Sorry, 1 for the big unit, 1,000 for the small unit. This means I'm dividing by 1,000, which is actually the same as moving my decimal place to the left 3 times. So I'm going to be ending up with a number much smaller than 30. And my final answer here is 0.030 grams. Don't forget that in dimensional analysis, we're analyzing the same piece of information with a new dimension. I know I have 30 milligrams. So when I analyze this in terms of grams, that small to big unit will take a big to small number. Big number, small unit, small number, big unit. Let's do another. Here I have a car traveling at 90 kilometers per hour. Use dimensional analysis to determine how many meters the car will travel in 15 seconds. This speed is a piece of information with 2 units. That means that this will act as a conversion factor for me. So I'm not going to start with this. Then I have this here, 15 seconds. That is 1 unit. So I'm going to try and start there. And then lastly, I know what I want to end up with. I want to end with meters. So I'll begin with 15 seconds. The only thing that I can do with 15 seconds is cancel seconds. Well, what will seconds go into? What conversion factor can I create? 90 kilometers per hour is not a conversion factor that works here because kilometers per hour does not have seconds. But I can take seconds to hours And that will allow me to apply this conversion factor to cancel hours. Before I get to hours, I'm going to go to minutes. I know how many seconds in a minute, and I can show then how many minutes in an hour. I want to pause here and point out that you can stop the calculation here, convert seconds into minutes, and now you have a new piece of information with just one unit. Now convert minutes into hours. Now you have a new piece of information with just one unit. Hours. Now convert hours into kilometers. However, this gets pretty tedious to do one calculation, pause, get an answer. Do another calculation, pause, get an answer. So I'm going to combine these conversions. I'm going to take my conversion from seconds into minutes. I'm going to go minutes into hours. And now that I'm in hours, I can put hours and kilometers, which is this ratio that I was given with my speed. But I'm not done, because I'm not interested in how many kilometers I will move. I'm interested in how many meters I will move. So I'll do one last conversion between kilometers and meters. We go through and we check that all of our units cancel. Seconds and 1 over seconds. Minutes and 1 over minutes. Hours and 1 over hours. Kilometers and 1 over kilometers. I started with one piece of information, 15 seconds, and I'm going to end with one unit in my information, some number of meters. Now we can plug in values. If our dimensions are not set up correctly to cancel, the values don't matter. So we should always focus on units, then come back and plug in our values. Big unit, small number, small unit, big number. Big unit, small number, small unit, big number. Now this is a speed, it's given to me. I have 90 kilometers per hour. Per how many hours? Per 1 hour. We don't say per 1 hour, but we know it's not per 2 hours. We know it's not per 24 hours. It is per 1 hour. Small unit, big number, small number. So we plug all of this in. A few ways that you can do this is to take the decimal, the fraction that each ratio gives you, and multiply everything together. What I like to do is multiply the entire numerator, multiply the entire denominator, and get one new fraction. So I'm going to take 15 times 1 times 1 times 90 times 1,000. Now I get this number, and I'm going to write it in scientific notation, 1.35 times 10 to the 6th over, I have 60 times 60, 3.6 times 10 to the 3. And remember, all of my units is canceled, so this is the number of meters. This just allows me to more easily do the division. If your calculator allows you, scroll up and select that first number, and then scroll up and select the second number. I will have moved 375 meters in 15 seconds. Let's do one more. An iron sphere has a density of 7.87 grams per cubic centimeter if the sphere's volume is 200 cubic centimeters. Use dimensional analysis to determine the mass of the sphere. 787 grams per cubic centimeter. 2 units, conversion factor. 200 cubic centimeters, 1 unit, that's where I'm going to start. And mass is where I'll end up. 200.0 cubic centimeters. I'm going to set up my densities so that cubic centimeters is on the bottom, grams is on the top, and I get 7.87 grams per 1 cubic centimeter. Now if we're checking, we know that we have much more than 1 cubic centimeter. We have 200 times that. So I should have much more than 7.87 grams. I should have 200 times that. If you've accidentally switched your conversion factor and you've placed it wrong, this little calculation check will help you catch that. All right, so I get a number here, 1,574 grams. However, I had a number that had 3 sig figs, and I multiplied that with a number that had 4 sig figs. So I really need to limit my value here to 3 sig figs. That means 4 is going to have a rounding effect on 7, and 4 will round 7 down. So I report this as 1,570. It's no longer 74, it's just 7D. If you're confused about that trailing zero, we can convert this in scientific notation where we can avoid that zero so that it doesn't look like a significant figure. It's not a significant figure because the number 1,570 has no decimal point written with it. So this trailing zero is insignificant. But we can show that it's insignificant by avoiding writing it at all. Now I want to take another example here to show how cubic values and squared values all work together. So in this example, I want to show you how to convert cubic centimeters into cubic meters. We'll take a step back first and recognize that there are 100 small unit centimeters in 1 big unit meter. And so a lot of people will think that this will scale 100 cubic centimeters to 1 meter. But let's see if that actually works out true. Let's say that I have something that is 5,600 cubic centimeters. And I want to do dimensional analysis so that in the end, I know how many cubic meters I have. And I do apologize, it has nothing to do with this example. Well, I want to cancel cubic centimeters. I can multiply that by 1 over centimeters. But that just cancels 1 of my 3 centimeters. So I'll need to multiply it by another 1 over 3 centimeters and another 1 over centimeters. So the relationship of meters to centimeters gets cubed. Another way of writing this is to say that I will need to use 1 meter over 1,000 centimeters cubed. That is the same as saying taking that multiplication 3 times, because saying cubic centimeters is the same as writing centimeter times centimeter times centimeter. So I take 5,600 divided by 100, divided by 100, divided by 100, and I find that in cubic meters, I have 0.0056 as my volume. If we had mistakenly used 1 to 100, we would have gotten a value of 5.6 cubic meters. We would have seriously overestimated our volume in cubic meters. Okay, so this has been a worksheet on dimensional analysis with a small emphasis on the significant figures that come with it. As you work on your problems, don't forget that some examples just may not feel applicable, and you can ask AI to try and limit the boundaries of where it pulls from, or you may use your discretion and simply not solve those problems on this run-through. Okay, happy studying.